part F in our L'Hopital's rule examples. This is the big finale. It's the last one I presented there at the beginning. The limit as x approaches 0 for the sine of x raised to the x. Okay. Well, let's go through our checklist. Is this simplified? Well, yeah. I mean, what are you going to do with that, right? Okay. Is it one of the indeterminate forms? Well, we talked about it at the beginning. Yep. 0 raised to the 0 is one of our forms, right? The 0 here is pulling it to 0. This 0 is pulling it to 1. Is it 0? Is it 1? Maybe it's something in between. We know we can perform the rule. Now, here we're really in a situation, right? We know L'Hopital's rule can only be applied to ratios, f of x over g of x. And here we've got sine of x raised to the x. How are we possibly going to rewrite that as a ratio? Actually, maybe this situation looks a bit familiar. When we did logarithmic differentiation, we had this situation going on, right? It was a variable raised to a variable. And how did we work around that? What function did we use so that we could move this variable down? Okay, so maybe you recall the natural log. So here's what we're going to do. Think of what's happening right there. Just call it y, right? Y equals the sine of x raised to the x, okay? Then, just like before with logarithmic differentiation, take the natural log of both sides, okay? And then that will allow us to move this x down in front like that. And then, once it's moved down in front like this, then we can rewrite this as a ratio. We've got the natural log of sine x over x to the negative 1. Okay. And this is definitely the way we want to think of it. Just move that x underneath like so. Now, one thing to keep in mind, we are trying to take the limit of y as x approaches 0. This is the natural log of y. So this really isn't the question, right? We've changed it. We took a natural log. True. What we're going to do is look at the limit of this right here. And we're going to need L'Hopital's rule for that, of course. But once we have the answer, we're then going to reverse the fact that we took this natural log at the beginning. Okay, so we'll get to that later. Let's first just look at how this limit would play out. So I'm going to slide this on up. Okay. So just setting it up, we're taking the limit as x approaches 0 for the natural log of y. Okay. And it's equal to the limit as x approaches 0, natural log sine of x all over x to the negative 1. We haven't done any L'Hopital's rule here yet. We're just setting up. That's what we're going to take the limit of. Okay. At this point, you may be thinking, hey, do we need to go through our checklist again? I mean, we did change it. We took a natural log. I suppose you could if you really wanted to be sure. But no, if we checked it at the beginning for sine of x raised to the x, then it's still indeterminate. It's still simplified. You don't have to do that again. If you're curious and want to look at it, you certainly can. But you've already checked it the one time. We haven't. All right. So let's apply L'Hopital's rule to the numerator, to the denominator independently. Here we go. So we write L'H equals limit as x approaches 0. And okay, so for the natural log of sine x, we've got a chain rule there. So if you remember, the natural log of x, its derivative is 1 over x. So if you've got the natural log of sine x, then sine x is what goes underneath. And since it's a chain rule, multiply by the derivative of your sine x. Well, that's cosine x. And there's your numerator. The denominator, x to the negative 1, well, that derivative would be negative x to the negative 2. Looking good so far. Okay, now, of course, our goal is to plug in that 0 and hope that we get an answer. But we don't want to do that yet. We want to simplify this first, because you never know. Okay, well, limit x approaches 0. All right. Cosine of x divided by the sine of x, if you recall, is cotangent x. And then we're writing our denominator as -1 over x squared. Now here's the thing. Let me slide this up. You might think, okay, we're good. We can plug in now. Actually, that's not the case. You're going to have problems if you try to plug in 0 for these. So the 0 down here, of course, then you're dividing by 0. And, you know, you could kind of think through that. Well, you're dividing by 0 and then the thing. We want to flip and multiply this and write it as simple as possible. And truth is, this is not simplified, right? A fraction inside of a fraction is not simplified. Even more than that, if you try to put 0 into cotangent, you're going to get undefined, say in your calculator. So we want to do a little bit more here. Okay, one thing we want to do, we can take this x squared way down here, and if you think of it flipping and multiplying, it will go up to the numerator. Also, since we are having problems plugging in 0 into cotangent, let's move cotangent down to the denominator, and this is what we'll have in the end. Cotangent moves down. We're taking a reciprocal, of course. It becomes tangent, and then that negative x squared goes up to the top, like so. Okay, hopefully you follow that. And then let's put the 0 in. Okay, well, what's going to happen? Well, 0 here, and then tangent of 0, you may recall, or your calculator might remind you, that the tangent of 0 is also 0. Okay, wow. So plugging in 0 over 0, or zeros, gives us 0 over 0. Oh no, we don't have an answer. There's a hole. Not to worry. This is on our list of indeterminate forms. And it is simplified. So what are we going to do? We got to use L'Hopital's rule again. That is indeterminate. But there's no way to simplify or anything, right? Oh, it looks like I picked it up on the next page. Okay, so when we apply L'Hopital's rule again, we'll do those derivatives. And let's keep this. I'll try and keep that on the screen. And here we go with the next line. Okay, so we got, oh, too many pieces of paper. Okay, so we're going to write L apostrophe H equals sign. Same limit, of course, limit as x approaches 0. And now derivatives. So negative 2x. And you may recall that the derivative of tangent x is secant squared x. Now that wasn't too bad, the way those derivatives worked out. Okay, now that we've done L'Hopital's rule a second time, we're crossing our fingers. Hopefully we can just plug in. If not, well, we can always do more. So plugging in the 0, or I did 0 there. Plugging in 0 for secant. So you may recall that secant x is 1 over cosine x. So if you put in 0 here, cosine of 0 is 1. 1 over 1 is 1, and then if you square it, you still get 1. So that's all. That denominator comes out to be 1. All right. So we got 0 over 1, and well, we know that is just going to be 0. Okay. Now we've done a lot of work, but it turns out we don't have the final answer. How was that? Hey, remember, this whole time we've been taking the limit as x approaches 0 of the natural log of x. We did that natural log at the beginning. Oh man. What we are really after is the original sine of x to the x, right? This was y. So what happens here? Well, you see my steps, and maybe you can kind of realize that looking at my work. We need to undo this natural log that happened at the beginning. Well, what's the inverse of a natural log? Of course, it's e. So we're going to take our result, and for this one, we're going to put it in the power of e. And there's our final answer, 1. And we got it. So when you do these, the case of a variable raised to a variable, right, do that natural log at the beginning. Then it's a lot of work. Don't forget to put your answer to the limit back into the power of e to reverse that natural log. And then you got your answer there. So who won the tug of war, right? It was 0 to the 0. And it was actually the exponent. The exponent pulled it towards 1 faster than this part could pull it towards 0. Right, it was sine x to the x. The x was going towards 0 faster than this was going towards 0. That's interesting. That's kind of bizarre. Okay. There it is. That is our section. Good luck. See you in the Zoom meeting.